right, I've got my calculator nearby and I've kind of talked about a heating curve of water. And what we need to do is to start thinking about each area of the graph and what it's representing. I'm counting 1, 2, 3, 4, 5 line segments in the heating curve of water. From point A to point B, A to B, I'm definitely seeing an increase in temperature, and this would represent for solid ice. When I'm looking at changing temperature, we know that MC delta T is the heat that we can calculate. From point 1 to 2 or point A to B, whatever you want to use for the dots on the graph, we're looking at an MC delta T problem for an ice. Keep in mind, my friends, that we have a different value for specific heat depending on the phase of our water. We know that when water is a liquid, 4.18 joules per Kelvin mole is our specific heat constant, but ice and steam will have its own value. We see a phase change in line segment B to C. From line segment BC, we are melting. The heat of fusion is what this is called. Line segment CD is changing temperature. So here we categorize this as heat of fusion. Here is an MC delta T problem where we're looking at liquid water. This is called the heat of vaporization. And clearly I can see vaporization, can't talk and spell. Clearly I can see an incredibly higher amount of energy needed to create a gaseous form from the liquid form compared down here to the heat of fusion. And of course up here we have an MC delta T problem for steam, gaseous water. So 5 different line segments, and each one of them is calculated just a little differently. So what we're looking at a closer value up here, the heating curve of water, when ice is warming, line segment 1, when ice is warming, it takes 0.941 kilojoules of heat energy for every mole to warm it up. Line segment 2, melting, going from solid to liquid, it takes 6.02 kilojoules per mole to cause ice to melt to liquid. Line segment 3, it takes 7.52 kilojoules for every mole of water just to warm it up. Line segment 4, 40.7, moving across here, 40.7. That's a huge number compared to the ones we've seen so far. By far the longest point or the longest segment of this graph. And line segment 5, 0.904 kJs per mole. Now, MC delta T is mass times specific heat times the change in temperature. We see that for line segment 1, line segment 3, and line segment 5. When we talked about specific heat of water, the C, it was in the liquid form, 4.18 joules per Kelvin. But what we're looking at now is already turning it into a mole, and that they've given us a kilojoule. That's why we're seeing a little different number here than what we're familiar with. It's different units. So let's take a peek. In line segment 1, by the way, you might want to keep this part handy because we're going to take one line segment at a time. Alrighty. Line segment 1 down here, moving from negative 25 degrees to 0. Because see, at 0, something magical happens with water. It melts. So I'm taking an ice cube at negative 25 and I'm inputting energy. And all of that energy being used is to warm it up from negative 25 to 0. If I had 1 mole of ice at negative 25 degrees Celsius and I heat it up to its melting point, MC delta T is how we'll calculate. Anytime you have a delta T, a change in temperature, where you actually have a slope on that graph, it's an MC delta T problem. They're reminding us that the molar mass of water is 18. And so they've taken, in other words, 18 grams times 2.09 joules per gram Celsius times the delta T of 25. Here's how we knew this answer. The specific heat of ice is different than that of liquid water. Liquid water was 4.18. This is 2.09. Each phase has a unique value. MC delta T gives us joules of energy. If we had 1 mole to move from point A to point B, 1 mole of solid ice warming up would take 941 joules of heat. Notice it's an endothermic process. It takes energy to warm something up. Line segment 2, again, keep referring back. Line segment 2 is going across a plateau. There is no slope, therefore there's no delta T. Therefore, it's not an MC delta T problem, but simple unit conversion. We pull out this value here, 6.02 kJs per mole. If heat is calculated, again having 1 mole, and it takes 6.02 kJs per mole, it's a simple multiplication. It would require 6.02 kilojoules of heat to warm up 1 mole, to melt 1 mole of solid ice and end with a puddle. Line segment 2, the heat of fusion. Keeping in mind the line segment, MC delta T, heat of fusion. Now we have MC delta T for liquid water, going up from 0 all the way to 100 degrees. That's a 100-degree temperature change, MC delta T. So in line segment 3, we're heating 1 mole of water, which is the same as saying 18 grams of water. Here's our familiar number, 4.18 joules per gram Celsius. And the temperature change is 100 degrees Celsius. And MC delta T shares with us 7.52 kilojoules of heat. Line segment 4. Go back to the graph, take a peek. Line segment 4, it's the plateau. Since we are not changing temperature, we have no delta T, therefore it is not an MC delta T problem. Instead, it's a heat of vaporization. Know that value, 40.7 kJs per mole. Simple cancellation. If it's 40.7 kilojoules and we're using 1 mole, we have 40.7 kilojoules to turn liquid water into gaseous steam. And the last thing we have to do in line segment 5 is to warm that steam up to positive 125 degrees. So this delta T is 25. 18 grams times the specific heat of steam times the 25-degree temperature change. And that's what they've shown you here. 2.01 provided for us for the specific heat of gaseous water called steam.